Okay, so we are live on YouTube. Test one, test two.
Hi. I, so I'm using for app. I'm using a different account, and on the upper part. So for the ad part, it is Ikasha 808. So the Twitter handle is the ad part, right? Or is it? Yeah. So that is Ekta Shah 808 instead, without space. I have joined it. Okay, respond. There we go. Okay. Okay. Awesome. Hello.
Hello, yeah, you are audible.
Okay.
Okay, so
Perfect.
shall we start?
Yes.
Yeah, okay, before that, Datta, can you give me a quick check on YT if everything is right on our YT stream? Okay. Hello everyone. I am Parth Pandya. I am co-founder of Zeta Gravit, and I welcome you to the fifth edition of XSpace. So, it is my distinct honor to welcome Dr. Ekta Shah, an astrophysicist whose groundbreaking research has shed new light on the cosmic cities in the early universe. Before we delve into the journey of these ancient cosmic cities, let me give you a brief introduction to Dr. Ekta Shah. Dr. Ekta Shah is a postdoctoral scholar in astronomy at University of California, USA. She completed her master's at IIT Bombay and her bachelor's at MS University, Vadodara. She recently discovered six large protostructures named Drishti, Surbhi, Shravan, Smruti, Sparsh, and Ruchi, which are essential cities of galaxies in the early universe. Today, we have the extraordinary opportunity to delve into this finding and explore the profound implication they hold for the field of astrophysics. please join me in extending a warm welcome to Dr. Ekta Shah. So, how are you, Dr. Ekta?
Hi, I'm doing great. Thank you so much for having me here. It is an honor to tell you all about my dive into the cosmic cities.
Yeah. So, like before we delve into the technical aspect of your research, let's start with your personal journey. So, could you tell us how you developed an interest in the field of astronomy and astrophysics? Did you get that spark during your bachelor study, or like was it something that developed even earlier, perhaps during your schooling? And like, how did your academic background at IIT Bombay and MSU prepare you for your current research?
That's a great question. So I have been always interested in astronomy, uh, and I think I grew up in the era of National Geographic and Discovery Channel. So when I was growing up, I was watching lots of documentaries, like space documentaries on these things. So that definitely enhanced my interest in this, and so I always knew that I wanted to go in research, and I specifically in this part, and to do that, actually, I wanted to go on the bachelor's of physics and master's of physics route, and then uh, go for specific astronomy route, because essentially in astronomy and astrophysics, you are basically applying like physics for astronomical systems, right? So it's very useful to have that strong foundation of physics itself. So that's why I decided to go for bachelor's in physics and master's in physics that I did from IIT Bombay. um, and you asked me how my that background prepared me for research. So actually, at that time, there were very few places that provided courses in astronomy. So this also includes IIT Bombay, in the sense that even at IIT Bombay, there were no astronomy courses. There were no astrophysicists working at IIT Bombay during 2013 to 2015 when I did my master's. So instead, what I did was I did actually my master's project at the TIFR, so Tata Institute of Fundamental Research. And so I worked on stars over there. Um, and apart from that, even during my bachelor's, so even though we didn't have astronomy courses at MS University Baroda, uh, what I did was I applied to lots of like astronomy workshops and winter schools and summer schools at different research institutes in India, like IUCA, NCRA, and also Indian Institute of Science. And also, so during my bachelor's, while I didn't do traditional courses in astronomy, I still had great opportunities to go to these places and participate in this kind of workshops and all, and interact with people, and have like proper astronomy background in that way. And then after that, I went to the Rochester Institute of Technology in New York, USA, for my PhD in astrophysics. And the reason why I chose that university was because all the courses were in astronomy. So, because at lots of places, when you have uh, graduate school in physics and astronomy, what they would have is they would have courses in physics and astronomy. So in that case, you will only have very few courses in astronomy, and most of the courses would be in physics. But because I had already done lots of courses in physics, I wanted to do lots and lots of courses in astronomy, and that was very useful to go to RIT and build my astronomy foundation there. And yeah, so my deep kind of interest, uh, from my childhood, combined with my strong physics foundation, and that combined with my strong graduate course in astronomy at RIT, really enabled me to do lots and lots of variety of observational astronomy research that I'm currently involved in.
Thank you for sharing your inspiring journey. It's fascinating to hear how your passion for the cosmos began and was nurtured through your experience. Moving on to your research, could you walk us through the process and methodology you used to identify and characterize the six protostructures? And please start with explaining what are protostructures so that those who don't know about it can know about it.
Yeah, um, so you might have heard the term galaxy clusters. So galaxy clusters are basically very massive and large structures in the universe where you have lots and lots of galaxies together in some ways. So you can have sometimes tens of galaxies to hundreds of galaxies or even thousands of galaxies in a very small area in sky. So you might have seen some pictures of galaxy clusters, and these clusters are usually in the local universe, so in the nearby universe. Now, when we look at when these clusters themselves were forming. So remember how I said like these are structures where you have lots and lots of galaxies together. So that's kind of why I refer. I use the term galaxy cities or cosmic cities. So instead of having like one galaxy here, one galaxy somewhere far, it's like lots of galaxies together forming a city of galaxy. But when this large structure in the universe is forming in the early universe. So in astronomy, as you might already know, that when we look at distant light, we are looking in the past, we are looking in the history of the universe. So when the universe was very young, these clusters of galaxies were forming. So the galaxies inside them were forming, and then this overall dense structure itself was also forming and evolving with time. So this kind of early phase of this cosmic cities or this galaxy clusters, that's what we call protostructures. Okay, um, and so what happens is when when we look at lots and lots of different types of observations of galaxies, because remember we have to uh, figure out, when you look at galaxies in the sky you will just see kind of 2D image, right? You will see like a picture of galaxy, but what you need to know is how many of those thousands of galaxies were kind of together in the early universe. And for that you need kind of this line of sight dimension. So in the direction that you are looking at, where do most of the galaxies lie? And that's very costly observations in terms of time and money, because we can only get that kind of detailed spectroscopic observations of very few galaxies at a time. So we use observations of lots and lots of observations from lots and lots of different types of telescopes, like the Keck telescope in Hawaii, Hubble Space Telescope, and sometimes also JWST observations. Also, in this case, we haven't used JWST, but we have plans to use that in the future. So basically, we take picture of sky and then figure out how many of those thousands of galaxies are together in the early universe. Then we use some novel method to figure out if they were together and what's the shape of that very dense structures where lots of galaxies are together in the early universe. And that's what we call protostructure. And the protostructures that I discovered, so I work as a part of the C3VO team at University of California in Davis. And so I work with Dr. Brian Lemo and Laurie Lubin and other C3VO members. And basically, as a part of this team, we work on different protostructure candidates. So we start with few observations and we think there might be something there, and then we target it with like lots of telescopes to know whether or not something is actually there. So initially I was working on just one protostructure candidate, and then when we took observations around it, I was like, there are more structures around it, there are more cities around it. And so we were very surprised, and then I measured the properties of these protostructures. So you can get the 3D shapes, and as a result the mass and volume and other properties of the structure. And when we looked at them, these are like very very massive structures. They have mass, each of them have mass of about 10 raised to 15 solar mass. So it's like 10 crore suns in each of those cities. They have lots and lots of galaxies. So if you want to show um on if you want to like share your screen and show the overdensity distribution of the structures that I have discovered. Um,
Yeah, we will display it on our YouTube. Yeah, it is displayed, I guess.
Sorry, I forgot that if you exit out of the app, it's just out. Um, okay, so let me really quickly open up YouTube so I know what you're looking. Hey everyone, in today's video. Oops, sorry. Um, so if you look at the 3D shapes, um, in the bottom panel, then that is basically the overdensity distribution of this structure. So the red part shows highly dense regions, and the blue part show lower density regions. So you can see these structures uh, in the local universe. When you look at galaxy clusters, they are kind of spherical because they are almost spherical because they are kind of already formed. But in the early universe, when the universe was very, very young in its childhood phase, you can see that the shapes of the structures are kind of all over the place. They have little clumps here and little clumps there, and you can see kind of clumps joining together to make bigger structure. So it was quite exciting to see this kind of different morphology or different shapes of the structures. And as I said, each of them have mass close to like 10 to the 15 solar mass. So very, very massive structure. They have lots and lots of galaxies in them. And for most of these structures, nothing was known before. So we were kind of the first one to measure all these properties and properly discover them and show their 3D distribution and all. So the thing is, it's very, very difficult to identify these structures in the early universe because, as I said, we need lots of different types of observations and very strong, very unique methods, which I'm fortunate that I got those things to actually make this discovery. And one more thing is, so because as I said, like nothing much was known about the structure, so it's kind of like we have literally discovered this structure. And because these systems are very unique, I also got to name them. So my postdoc advisors here were, because you have discovered it, you would have honor to name them. And so I uh, initially I was thinking about, you might have heard about a large superstructure that was discovered by NCRA team, and they had named it Saraswati. So I was kind of thinking on those, that in this direction, but then I decided to give the structures names that are inspired by names of our six senses. In different Indian languages like Sanskrit and other Indian languages. So I decided to give them names of Drishti for vision, Surabhi for smell, Shravan for hearing sense, um, and also Sparsh and Ruchi for the last two structures for touch, and Ruchi means taste in Telugu. And then for one of the structures, I decided to give it name of our sixth sense. Um, but I decided to choose the name of Smruti for that sixth sense. And Smruti, as you all might already know, literally translates to memory. But the way I interpret it is, your intuition is kind of, uh, it's something that's embedded in your DNA, right? It doesn't come from logical reasoning or something that you see. So your intuition, your sixth sense, is something that's embedded in your DNA. And how did it that get into your DNA? That's through uh, that's through your ancestors, right? So it's kind of like ancestral wisdom that has transcended time, and that's embedded in your DNA, and that sometimes guide you, because your intuition is kind of like, something that our ancestors have learned throughout, their lifetime and their wisdom. So it's kind of their wisdom that guides you, and that is kind of like your intuition. At least that's how I see it. Um, so that's why I decided to give it name of Smriti. And it's this is also one of the this is the structure that we had intuition of, and that intuition led to this discovery. So I named it Smriti. And the reason why I decided to go on this route of six senses is also because we are we are literally part of the universe that tries to understand the universe, right? And these senses are kind of like our first contact with the universe, and through these senses we kind of experience the universe and understand it. So it's kind of honoring these senses and honoring um, our capacity as humans to kind of curiously see the universe and understand it. So yeah, I hope that made sense.
You are truly rooted in your culture, and that's a great thing. It's amazing to hear and study names that are Indian because we don't get to study those. So now, could you share with us the challenges you encountered during this discovery, and how did you manage to overcome them?
Yeah, exactly. Exactly related to the point you mentioned about not seeing lots of Indian names, because most people, you know, m- most people in Astro are still kind of Western people, and they would choose, like, you would usually hear names that are like Greek or Latin and all. So even me working in this field, I very rarely see like Indian names. And then that's why I kind of decided to give them Indian names. And also I presented this discovery in various conferences in Italy, Netherlands, and also recently in Iceland. And as I said, like, these are really amazing systems. So there, people who are from this Western countries like USA and all this European countries, um, they they really like these systems because they can ask their own scientific questions and see how the systems would behave. So they have already started using these structures in their analysis. So one of the things that I was really happily surprised to see was the names of these structures in kind of recent papers and proposals. So it's very nice to see, like, when you see research paper of some Western authors that have nothing to do with me personally, but they are using these names of Sparsh and Smriti, and also that was amazing. Um, and so you asked, like, the challenges we faced. So as I said, like, so the field that we used, that has been studied, like, that area of sky has been studied for a long time. But even given that, these structures were not known. So that tells you, like, while you have hundreds of people working in that same area of sky, how difficult it is to identify these massive systems. Because if this was very easy to find, people would have already found it. um, and so, as I said, as a part of the C3 view system, while we initially had intuition about one system, we targeted using the Keck telescope in Hawaii. And also, I combined lots of different types of observations. And then we used this very incredible method that my postdoc advisor has developed. And through that, we were able to kind of actually look at, like, proper extent of these structures and measure their properties. And also, like, for example, the one that is the farthest away, uh, the highest redshift one, as we would call it, there is absolutely no mention of it anywhere else. The structure that I have named Ruchi. So that also tells you that, again, this is a very, very massive system, but it was so difficult to find it, that it's only now with these observations and techniques that we are able to even see the structures. And also, our team has now we have we applied for JWST observations of this structure, and that JWST proposal is also accepted. So in the upcoming months, there will be JWST observations of this structure, and as a result, more information will be found. Um, I will also add, so I mentioned that, these are cities of galaxies that are in the formation phase, right? Now, why why do we want to study it? Okay, so let me provide a little bit of more motivation for that. So the thing is, in the local universe, as I said, in the nearby universe, you have this kind of clusters of galaxies, right? Now, as you might already know, so if you are a person who lives in like big cities like Ahmedabad, Mumbai, or Delhi, right, there will be many things that are very different of people who live in cities versus people who live in like small villages that are kind of far away from the city. So similarly, when you look at galaxies that live in cluster in the nearby universe, the environment of cluster is so dense, and there are so many processes related to this dense environment, that as a result, the galaxies that are in clusters, they show very different behavior. So typically their star formation rate is very low. They are very massive. Their black hole activity is very low. So in the nearby universe, the clusters of galaxies, the dense environments of clusters, they seem to be suppressing or lowering the star formation rates of galaxies. Now, interesting thing happens because when we look at this early systems, this early protostructures, that behavior is completely different. Okay, so one of the studies that I'm doing right now, which hasn't been done at this epoch in the universe, is when I look at the galaxies in this early cities, they show actually higher star formation rate, higher black hole activity compared to things that are kind of far away. Um, so early cities of galaxies seem to be increasing the star formation rate and black hole activity of galaxies. So it's a very different behavior. So it's kind of very interesting from physics standpoint, like exactly which processes happen in the early universe that are completely different from what happens right now. So why do this dense environments? They decrease the star formation rates in the galaxies right now, but when we look in the early universe, they were increasing the star formation rates of galaxies. So this role of environment is very different in the early universe, and that's why these protostructures are kind of like really great laboratories to study exactly what's going on. Yeah.
That's interesting. Like when we consider the scale of galaxies, it becomes clear how challenging it is to locate Earth within them. The fact that amidst these vast cities of galaxies, no one has been able to spot Earth underscore the magnitude of your discovery. Your hard work is truly appreciated. Now, how do these huge structures contribute to our understanding of galaxy formation and evolution in early universe? Specifically, how do their characteristics and environments provide insight into the process shaping galaxies during this crucial period?
Right. So that's kind of related to uh, things that I described right now. That uh, you have to remember that galaxies themselves were also forming in the early universe, right? The universe may seem like a static place when we look at the sky, like nothing is moving much, and galaxies are just kind of there. But when we actually use the observations of like deepest part of sky and observations of systems that are far away, you see that as we go into past and past, galaxies were literally in the formation phase. So you look at like the gas in galaxies. So right now, most of the gas in galaxies is kind of already used for star formation rate. But when we look in the history of the universe and consider galaxies there, lots of galaxies were still forming lots of stars because there was a lot of gas available. So in the early phase, when galaxies, when they didn't have their disk developed, they didn't have all their stars formed, when they were still forming, and then if they are living in this dense environment, so at that point, this dense environments seem to be helping them to bring more gas to them, to cool this gas down and form lots of stars, and also to push this gas towards the center of galaxies and trigger their central black hole activity. Okay, so this dense environment play a very crucial role in the formation and evolution of galaxies in this early universe phase. Yeah.
Yeah, so the discovery of this massive protostructures is indeed significant for our understanding of universe. So, like, how did you name this protostructure? Like, why you choose six senses, like five senses and all? Like, was it something related to the like senses of the universe, or maybe because of telescope, or like something that like you understood the question, right? The philosophy behind naming this structure.
Yeah, yeah, yeah. So, like I said, that I find it, I, f- I find myself to be very privileged to be able to do that, because look, we are humans, right? When we compare the scales of these systems, even like scale of Earth, right? Scale of Earth, let alone scale of galaxies, it is so vastly different from human scale, right? So it's kind of uh, it's almost unbelievable to me that we as freaking tiny uh, sorry, as tiny humans get to kind of somehow, take observations of this crazy systems that are far away in the universe, and then using basically just the light of these systems, right? Because in astronomy, all you have is light. You don't have anything else, right? The galaxies aren't like, coming close to Earth and we get to kind of actually take samples of it, right? But somehow it works out so well that the lights from this far away galaxies in the early universe, we get to kind of take observations of that, and that tells us like how many stars are forming, where they are, where these galaxies are located, and all sorts of things about these galaxies. So in a way, like these telescopes are kind of like our sense, right? It's our human vision that is extended and expanded in space, that we get to kind of see these things. And then we can also, not only we get to see it, but we also get to comprehend it, like what does it mean, and um it's also kind of good to keep in mind that just about like 100 years ago, we used to think that our galaxy is the entire universe. Okay, because we didn't know, while people had taken observations of some nearby galaxies, we didn't know how far these galaxies were. So we used to think like the size of the universe is the size of our galaxy, and what looked like to other galaxies were just kind of tiny nebula nearby, right? And then we were able to measure this distances better, and we are like, no, these are really big systems that are far away from these galaxies that we call our galaxy. So it's kind of very interesting to me, like how uh like if you were a blind person, right? We can't even, people who can see, I can barely imagine what it would be like to be like a blind person, and how drastic your worldview would be, right? I mean, even blind person have like different senses, so that's a very different argument. But the thing is like how your worldview completely changes if you remove one of these senses. Okay, so it is through the senses that, let it be like a tiny atom, let it be, Newtonian principles, or let it be these galaxies. It is through the senses that we actually get to see the universe and comprehend it. I mean, there might be something more, because we haven't talked about like what does it mean to be conscious and all, right? But you still need, it seems like you still need these senses to get the information from the universe and then somehow interpret it. Uh, so that's why I kind of wanted to honor this census, because, yeah, without that, it seems very difficult to do all the stuff that we get to do, and and
Oh,
and,
that's
and also related to, sorry, one minor point related to what you said, right? It's like, are this senses of us as humans, or are this senses kind of like senses of the universe, right? Because we are literally part of the universe, right? We are, in a way, like we are literally, all the stuff that we are made of was made like inside star, or when the star collapsed or star exploded, right? So um in a way, we are literally like part of the universe or extent of the universe. So in a way, this is like universe using its senses to somehow know more about it, you know.
yeah. Like I remember the line or the quote that Carl Sagan says, "We are the stardust that shines."
Yeah.
So I would like to read it with this. Okay, so now what are the next steps in your research following these discoveries? How do you envision this finding influencing future studies in astrophysics?
Yeah, great question. So like I said, because these there are very very few systems at this early universe that are already known, and that's why this discovery is very important, so that we can answer the questions that are raised, like what are the processes, why is, first of all, the behavior of the environment and its impact on galaxies is very different. That itself is not completely known, like I'm still completing that study. So the thing that I mentioned, that how this dense environments in the early universe seem to be increasing the star formation rate and black hole activity of galaxies, I am completing that study. So most of the people who work in this field, they still don't know about this. And on top of that, because we have the structures now, people can ask their own questions and try to see how this the galaxies in this system behave. So for example, some people work on quenched galaxies, which is like when you have star formation of galaxies that is completely low. So suddenly if galaxies stop forming stars, which happens a lot of time in the local clusters, is like, why does that happen, and how is that different in the early universe? So now that people know these systems are there, and I have provided like the locations of the systems and other properties of the system, so people can themselves kind of check, like if I ask this scientific question, like how does the suppression of star formation rate or the quenching of star formation rate uh, is done in this systems, they can kind of carry out their own scientific analysis. So that's why like giving this kind of laboratories to the scientific community is very important, so that lots and lots of different scientific questions can be asked and answered. Um yeah, and for me personally, as I said, I am completing a study on how the black hole activity is different in this early environments. So I'm currently completing that research paper right now, and yeah, and as I said, there will be lots of more questions that we can ask. Another thing is also, even within the six systems, some of the system, for example in Smriti, we do see this increment of star formation rate and black hole activity, while some other systems they don't show as much increment. So there is also that question of like, which systems show much and much boosting of this processes like star formation rate and black hole activity, and which systems don't, and if they are showing, why are they showing increment? Because in the nearby universe we don't see increment, we see kind of lowering. So if in the early universe it's increasing, why is it increasing, what are the processes? So we are also collaborating with people who work in simulations, in cosmological simulations of galaxies, to see if in simulations also this thing happen, and what are the processes. So you have to kind of combine observations and also simulations to get the full picture of processes that are responsible for this kind of behavior.
So yeah, like your research plan for the further exploration sounds quite thorough. Now, like we know, every new discovery in science brings forth the new problems to solve and questions to answer. So, with this discovery, what new questions have emerged that you are eager to investigate further?
Yeah, so one of the thing is the Asian activity part that I mentioned, and another thing is also that my colleague is working on is how does the if you look at like the mass distribution of galaxies, that is also very different in this dense environments compared to galaxies that are more isolated. So as I mentioned, like in the clusters in the local wide universe, you see lots and lots of massive galaxies. Okay, and similarly, even in this protostructure, you see kind of more massive galaxies. So that entire shape of like how many galaxies are at, for example, 10 raised to 10 solar mass versus 10 raised to 10.1 or 11 solar mass or 10 raised to 9 solar mass. So that if we kind of plot it and look at that shape or the mass profile of galaxies in this universe, that is also very different in these dense environments. So that's one of the things that we are kind of studying apart from the star formation rate and black hole activity. Um, and we are also kind of studying like the specific star formation rate. So if you say like per unique mass, how many galaxy stars are forming, how many stars the galaxies are forming. So that itself is also very different. And um, this dense environments also seem to be increasing that. So there are lots of puzzles like why is this behavior very different? Why is this behavior very different? So we are trying to understand all those different questions and what leads to them. Yeah.
That's interesting. Keep us updated with it.
Mm-hmm.
Now, as a woman who has been into the STEM for quite some time, what message do you have for women who are currently in STEM or considering joining the field?
Um, I don't necessarily see myself as like woman astronomer. Um, I would say, I mean, astronomy is definitely one of the fields where there usually there are more women than men. Um, and even the people that I have interacted with so far, I think I have been like fortunate enough that uh, it hasn't nobody has like treated me differently as far as I can tell because I'm woman, or I didn't have to face any issue. uh, and I mean, in physics it's kind of interesting because astronomy is part of physics. In physics there are relatively less number of women, but then in astronomy there are more women. So just to give you an idea, like when I was in IIT Bombay, there were 6 girls out of class of 40. Okay. uh, so it does change quite drastically from physics to astronomy. I would say overall, the field of astronomy, astrophysics, people are very very supportive, very very understanding. And there are also, if you go to different facilities like different telescope facilities, and if you are working there, there are also women specific policies, like you can get really good maternal leaves or something. So the field is really rapidly evolving to make have more women in long term careers. um, and I think one thing I would say that uh, even if you are a woman and you are looking for a career that doesn't have many movements, don't see it as necessarily like a strongly negative thing. I think i think sometimes, especially in the recent era, we are kind of, especially in the western world, it's like people would very quickly say that there is a lot of kind of uh, lot of things against women, like, and men don't want women or this and that. But I think sometimes we also do forget that men and women are in some ways different. So there can be different choices that most people make. So most women may or may not like, very like mathematics or physics or something like that. I'm not saying that that is the case, but you can imagine like how most men wouldn't like to be in like makeup industry, right? So there can be some choices. And one thing is, there is one thing that is average and there is one thing that is outliers, right? So even if Even if, let's say, 99% of women aren't going for some career, that doesn't mean that you as a woman can't do that. Okay, because there will be always outliers, so don't apply the general statistic on yourself, that just because most people can't do it, I don't know if I can do it, I don't know if this field is safe or not. Okay, just consider yourself as an individual, consider yourself as a potential professional in that field. Okay, I wanted to be an astronomer. I didn't want it to be like, oh, I have to have like 10 women around me or something. Okay. And another thing is, as a woman, one thing that we have to look out for is women. Like nowadays, women are much more outspoken, but we do have that innate characteristic of like avoiding conflict and not being, not saying things when necessary. So I would say that have your boundaries very clear in your mind. And also, if you're interacting with somebody, and if somebody crosses boundary, make it very clear it's not acceptable. And things are, a lot of things that used to be acceptable and that were not good uh, are no more acceptable. And so a lot of places are much more safer for women. And you can also, like, talk to people if you have some issues. And also, the world is much safer for women, and take full advantage of that, and speak up when necessary. Absolutely. Conflict conflict delayed is conflict magnified. Always remember that. So if something needs to be said, say it. That's what I will say.
Yeah, like that's really interesting perspective. I hope fellow women will learn from you. Okay, no more questions from my side. So, again, thank you for that inspiring message. Your
Yeah.
work and achievements are testaments to the valuable contribution women make in STEM. In conclusion, your discovery of six massive protostructures are your and your innovative approaches to studying them have not only advanced our understanding of early universe but also served as a beacon of inspiration for inspiring scientists who are looking to make their mark in the field of astrophysics. So thank you once again for sharing your insight with us today. Now I guess we can move for Q&A round. Like we have some questions. So first of all, our teammate Datta is requesting you to keep your work updated on X regularly. So
Yeah.
would you
Well, I
like to
joined
answer
today,
that?
so I will do that. Yeah. Uh,
Yeah.
my profile is non-existent
Okay.
right now because I just joined, but yeah, I will do that. Good suggestion.
Yeah. And like else you can also give us like we can do collaboration and we can publish your work too from our platform.
Thank you. Yeah, I really appreciate it.
Okay, so next question is from Preet. He is uh, like he wants to know more about that JWST thing. Like what are the backend processes which are going on? Like if you are allowed to share.
What are the what?
JWST, like you said now that you have
Haha,
applied
the
for
proposal.
JWST. Yeah,
Yeah.
that.
Um. Yeah, so like I said, that the structure that is farthest away, Ruchi. So there was no mention of it in the scientific literature so far. So this is literally the first time that anybody has seen it and anybody is studying anything about it. So we have a lot of information about it, but it still has relatively less number of galaxies. Like we don't know, because this is when the universe was like only a few billion years old, maybe like 2 or 3 billion years old or something. So very early part. So what JWST can do is, again, if we target galaxies, lots of galaxies, then they would know that how many of them that are together in this very early phase. So right now we have identified around 11 galaxies that we are very very sure about, and then there are still lots of galaxies, like hundreds more, that could be there, but we don't know yet. So if we target those galaxies using JWST, we will for sure know if they are also in this structure, and then we will be able to characterize it better. Like how far does it boundaries go, how much massive. I mean, we already know the mass, but once you know, like, instead of 11 galaxies, like, you have this 100 galaxies that are together, so you can better characterize that. So that's why we have applied for JWST time, and it is very competitive. So the way it works for this big telescope is people from all over the world can apply for the telescope time. So they would say, some people would say, I want to observe this particular star or this particular planet or this particular galaxy. And out of all the proposals, very few proposal get selected, because the telescope time is extremely valuable. So you have to provide kind of like background that why you think this thing is very important to study and how it will be helpful for the entire scientific community. So we provided that, and that was sufficient enough that we were awarded the JWST time. So our colleague Lucian, Dr. Lucian, who is at Texas University, so she got the proposal time, and once we will take observations using JWST, we will be able to better characterize this structure and know detailed information about it.
And like how one can apply for this telescope time?
Yeah, so for JWST, actually, anybody in the world can apply. The thing is, if you are enrolled in a US university, then if not only if your proposal gets selected, then you get time, but you also get money associated with it, in the sense that, like, if you want to hire a postdoc, or if you want to hire a PhD student, or if you want to support yourself. So for example, if I was the PI, or the primary investigator, principal investigator of this proposal, then depending on how much time I'm getting on JWST, I can be like, I want to be, at UC Davis, and I want to, for a year, I just want to study this. So I can also support myself, or if I want to hire like a PhD student or something, I can do that. So, but anybody in the world can apply for JWST. So if you go on the JWST proposal page, there are kind of guidelines, and they also provide list excuse me, they also provide list of all the proposals that have been selected. So that will also help you kind of get idea about what typically gets selected, how do they describe like their science, their technical things, and even the technical things, their overall website and other things would help you, that if your galaxy is this bright in some observations, how much time will you need, because the JWST is very very new. So like, we don't know all the technical details offhand, like all the astronomers, you have to use this online user interface that allows you to put some information about the galaxy that you already know, and then that will tell you, like, if you want to observe using this instrument on JWST, how long it will take, or uh, yeah, like the specific, it will help you determine the specifics of the observations, and that you can put in your proposal, like, are you requesting for 5 hours, are you requesting for 80 hours, are you requesting for 100 hours. So because remember, in astronomy, again, all you have is light. So sometimes if you are trying to observe very faint objects, you will have to take observations for hours and hours, and then kind of combine them together so that you can have some useful information. So depending on your object, you can request for how much time you want, and then the telescope time allocation committee would decide whether or not, your proposal is good enough. And sometimes you request for lots of hours, and they will give you, like, maybe it is possible in 80% of time that you requested, so it can vary a little bit, but yeah, it depends on what you want to study, and whether or not you can make strong enough case for it.
And like who will decide how much hours should we give to which activity? Like which committee specifically?
Yeah, so it's called TAC,
the telescope time allocation committee, but it is made of astronomers. So the way it kind of works, it varies a little bit from telescope to telescope, but typically uh, they usually have different divisions like planets, stars, then galaxies, sometimes also AGN or active galactic nuclear black hole ones. And sometimes they also have this kind of large clusters or large structure system. um, so ours kind of fall in between the large structure and galaxies, because while we are interested in large structures, we actually want to target galaxies. Versus sometimes you want to, like for example, look at like the extra distribution in the entire structure. So that will be a very different proposal. So there are different committees related to this categories of galaxies, planets, and stars. And then, for example, if you are in galaxy category, then it will have certain number of astronomers, uh, typically from US, but it can include sometimes international people too. And then the way it works is, so I can have my imagine there are like 20 astronomers, right? So each of them or some of them might have already submitted their own proposal, but the way it works is uh, I don't evaluate my own proposal, but others evaluate my proposal, and I evaluate, like, all the proposals that's get in. So there are sometimes hundreds of proposals and very few get selected. So basically, each member would evaluate certain number of proposals, and as a result, each proposal would be evaluated by like three members or five members, and then you have to write like which are the strong points, which are the weak points, and you have to give it certain number, like out of five. What would you give like score on technical things? What would you give score on like the background information? How strong would you think this is useful for scientific community, and how strong of original contribution this will be? So there are different parameters on which you have to scale the proposal, and sometimes you kind of discuss this in the panel. Once you have evaluated it, panels can kind of make argument, and some other times there is no discussion, it just kind of averages out. So it kind of depends. And that's why it's kind of somewhat there is a little bit of luck element involved, because it's like, something that I find very interesting may not be that interesting to you, right? And sometimes something is very interesting, but I don't know if I can make strong enough case for that. So there are that kind of a little bit subjective things involved, but on an average, the tags try to kind of balance things out. That's why you don't have just one person deciding who's gonna get time. It's like entire committee, and they make a decision of which proposals will be getting selected.
Oh, nice. Like
Yeah.
we were not knowing this about before. So there's one more question from Preet. He says like, what are the technical paperwork and all the processes you go through while naming of protostructures?
Uh, yeah, so one of the main thing is, as I mentioned, that we need lots of different types of observations. So I mentioned that we used quote unquote spectroscopic observations from Keck. Uh, so that was part of C3VO survey, but we also kind of took lots of observations from other telescopes, and a lot of people, as I said, this field has been studied for, excuse me, for a long time. So I also combined the observations that were taken using other telescopes in sky, like Hubble Space Telescope, then some telescopes in Europe. And on top of that, because we are also interested in like how massive this system is and how massive the galaxies in it are, and how much is the star formation, so we are interested in all these different things. And for that, we need multi-wavelength observations. Okay, so we need like optical observations as well as like x-ray observations, then infrared observations. So and they kind of come from some of the space telescopes like Chandra's Space Telescope, X-ram Newton Space Telescope, or Herschel Space Telescope. So all these different kind of multi-wavelength observations will tell you kind of slightly different things about it. So if you look at like infrared observation, that will tell you how much dust there is, and some other observations will tell you how many very massive old stars are there, how many new stars are forming. So it's kind of like, if you use x-ray, if you take x-ray of your hand, that will give you very different information from your camera of your phone, right? Because with the camera of your phone, you cannot actually see your bone structure, right? So similarly, for galaxies too, when you have new stars forming, they emit somewhat different light compared to old massive stars. So if you combine all this information, that will tell you how massive the galaxies are, how many stars are forming, what is the black hole activity, and all that. So we kind of combine all these observations that are presented in different papers using different telescopes, and we kind of combine them for our study. Uh, yeah, I hope that kind of answered
Yeah.
the question.
And I guess he was asking about what are the processes, or like how basically we register name of particular object in space which we have discovered.
Oh, I
I
see.
guess he was asking about that.
I see, I see. Uh, so that these are kind of like colloquial names. So these structures already have like somewhat technical names that are based on their location, and this colloquial name, there is no particular place which is like this is the official name, but the way it kind of works in practice is, so because I have discovered this structure, it's like every paper that will use this system from now onwards, if they are being, completely transparent and authentic and doing what they should do, then they would cite my paper. Okay, they would say that this structure was originally reported in Shah et al. 2024. So this, my research paper is now published in the Royal Astronomical Society journal. So people can cite my paper, and then they would start using the names that I have given. So that's why it was nice to see uh, the names that are already getting, like the names that I have given, people have already started to use it, which means it's kind of accepted in the scientific community. Um, but I mean, it's not like absolutely necessary. So somebody can still kind of publish on this, and uh, don't use these names. But so it's not like strongly enforced, but it's more kind of organic. Um, so yeah, it was kind of nice to see everybody using it. But I mean, it's like if you have discovered something, right? And when I write my paper, and if I don't say that this is the first person that had discovered it, right? So sometimes it's the part of the uh, reviewer. So as a reviewer, I would say, if you submit your paper and you haven't cited some of the main papers, like this kind of discovery paper, and if I know about it, I would be like, this is absolutely necessary. But sometimes if the reviewer doesn't know, it can kind of get passed away. So you will have some papers that haven't cited like the original discovery papers. So it can happen, but in practice it's a relatively smaller community of like few hundred people. So like I was in conference in Iceland, and the person who writes like a review paper of this entire field, he has already started using my structure. So he presented, in his presentation he included my structure. So it's kind of like, because there are not like thousands of people working on these protostructures. People know that, people who work on these structures know that this is the discovery paper, and then they kind of cite it and use this name. So it's very organic, and it usually works out.
Thank you for sharing this. Now we have question from Sasikant. He
Mhm.
says, what are some composition changes observed in elemental chemistry in identification of protostructures?
Okay, that's a great question. So galaxies themselves typically were less metal rich in the past. So you can imagine that the way the different types of element increases. So in astronomy we call everything that is not hydrogen and helium as metals. So keep that in mind. So the way the chemical enrichment of galaxies happen is through stars, and when you have stars forming metals inside them, and also when you have explosion of stars, like supernova explosion or collapse of stars, that's when most of the chemicals or most of the elements get made. And for that, you can imagine that over time you will be forming more stars, and more stars would be dying, and this process will keep repeating itself, and that's how you get chemical enrichment of galaxies. So you can imagine that in the early universe, when galaxies were still forming, and most of the stars that we see right now hadn't started to either form yet, or if they had formed, they were in very early phase. The enrichment of galaxies was very low. uh, so it was much lower compared to what we see right now. But in the protostructures, I think that is also one of the question that will be very interesting. You need much more detailed observations for that, because the observations that we use right now, it usually has very few emission lines. So we know sometimes we see like oxygen emission line, and hydrogen emission line. Sometimes we see nitrogen, or sometimes we see sulfur, but mostly it's oxygen. So uh, if we want to know about like iron content or some other things, you will need lots of more different types of observations, and that's partly why this kind of JWST observations would be useful to ask this kind of more detailed questions. So that will be interesting to see. uh, and I think it would be different, but it's kind of interesting, like what would it be? Is it gonna be higher compared to the background, because galaxies are forming stars rapidly, or is it still gonna be lower because the star formation hasn't caught up yet with the background, so it's a very interesting question. Thank you. But it
We
remains to be
have one
seen, so
more.
maybe you can submit proposal for that.
We have one more interesting question from him.
Yeah.
He says, "What's the information loss and information gain density of early universe till now? If we probably do a Bayesian statistic to scale the fitting of data under ROC curve." Like before answering this question, please explain all the terms. Like even I don't know about that.
Well, the technicalities of these things, even I'm not sure in which context it is mentioned in terms of like information loss. I understand maybe the Bayesian statistic part, uh, but I don't know in which context this is asked. Could you expand? The person who asked this question, can you expand a little bit on that? Because we don't use these terms regularly in Astron, at least in my area.
If possible, is it possible? It is possible to you for unmuting. So like unmute your mic and ask your question. That would be better, I guess. Okay, so like we have one more question from Preet. He says, "What kind of instruments you have encountered till date?"
Yeah, that is also a great question. So, um, instruments, as in, I'm assuming like for taking this kind of observations, right? So that is a great question, because you do need different types of instruments to get different types of observations. So, for example, if you the instrument that we typically use for this kind of spectroscopic observations of galaxies, it's called DMOS on on the Keck telescope. So it is basically what we call multi-object spectrograph. Okay, and for that, basically we have like a metal sheet, and in that there are tiny holes. Okay, so you can decide that in this entire in this in the area of sky, you can drill holes where your galaxies are. So you can drill holes that you can have like you can have thousands of galaxies in field, but I am interested in 100 specific galaxies. So then I drill holes there, and what happens is this instrument is attached with the camera of the telescope. So what happens is light goes from the telescope to the instrument and then to the camera. And so basically, as light goes through these holes, as these lights of specific galaxies that you have chosen goes through this hole, it goes through kind of spectrograph, which is kind of like, how when you have prism and it divides the white light into multiple colors. So spectrograph would divide the light into very detailed spectrum. Okay. And in that, you will be able to see this kind of emission lines or absorption lines. And depending on where those emission lines are, that will tell you how far the galaxies are. And that will tell you how far is it moving away from us, and therefore, like, what is the distance of the galaxy from us. So that's what we want to use. And through this instrument, we can get this kind of observations of 100-ish galaxies at a time. But this is also very different from the typical telescope or imaging telescope, because in that, if you're just taking picture of sky, it can have thousands of galaxies together. Okay, but in that, you don't get this kind of very detailed spectrum. So it will give you some information about like how bright the galaxy is uh, in like red color or green color or other blue colors or something. But if you want to know precisely how far the galaxy is, then you will need this kind of spectrograph. So that will reduce. In general picture, you can observe 1,000 galaxies, but in spectrograph you can observe like 100 galaxies together at a given time. And that too, you have to observe it for hours, okay, because these are very faint systems. So that's why I said it's very expensive to take like to take spectroscopic observations. Because just to give idea, the cost of operating and using Keck telescope per night it's like $50,000. Okay, so for 2 Keck telescope, it's like $100,000 per night. Okay, so it's almost like 1 crore rupees per night. So it's very, very expensive. We don't have to give that money out of pocket. It comes out from different grants or from university or this different NASA. So the research that I have done, it was funded by NASA. So my postdoc salary as well as all my research stuff that comes from NASA. But University of California, I also have advantage because University of California do own certain percentage on Keck telescope. So then they have their internal review of different University of California proposals, and some of them do get selected. So we have that advantage. So University of California gives some funding for operating Keck telescope. So, but yeah, so that's why spectroscopic observation is very valuable, but it's also very expensive in that way. And that's the instrument that we typically use. Lots of spectrographs.
So Sasikant says he has done some black hole simulations in Python, and he has observed the exponential curve for energy versus epoch density, and there is some error rate of 3% of information loss. Any optimized trial runs that he needs to perform?
I am not sure. Could you repeat? I think I missed part of it.
Like he has done some black hole simulations in Python, and he has observed the exponential curve for energy versus epoch density, and there is error rate of 3% of information loss. So like he's like asking for any trials which he need to perform to uh, probably get the
Yeah.
data or result.
I don't work in that area, and I know like the information loss term and all that is related to very theoretical side of black hole. When I mention black hole and the work that I do, it is more like when you observe this active what I call active galactic nuclei, which is very massive black hole in the centers of galaxies that is very active. So what we do is, if you have galaxies that show very strong X-ray or very strong emission in some other band, then we say that it has very active black hole, and then we measure that, like for example, what is the total brightness of this thing. Okay, and then we say like out of 100 galaxies, how many galaxies show this kind of very bright active black hole. So that's the analysis that we do. We don't go into too much specific detail, especially theoretical details of black hole that uh, he is talking about. So that is not my area of expertise.
Okay, so any more questions? Like he says, information loss and gain is the energy loss of black holes observed till now. Any optimization techniques we can embed to restrict the parameters for observation with the goal of bring less wrong rather than how good the prediction model. Okay, so any more questions?
I would suggest this person to email me, and maybe we can have like a detailed discussion, because it seems like there could be some interesting collaboration, because they seem to be working on more on theoretical side, and I am working more on like actually observational side, because a lot of times you can have very detailed theories, but in practice you can only observe certain things, right? So I think those kind of conversations can be actually very useful to see what you can predict from theory and which observational parameters you can use to test this theory. So I would suggest this person to send me an email on eashah@ucdavis.edu, and maybe we can have a detailed discussion, because I would love to know more about their work and how we can use the observations maybe that I have or other observations to check this and improve it. And yeah.
So I guess we we don't have any more questions. So thank you once again for giving your time and effort. Like we were planning this from last 1 month. There was delay, but okay, fine. Okay, so once again, thank you. Thank you for joining us, and also thanks to all the participants who joined. There's one small announcement. We are hiring. We want contributors uh, for creating our graphic and content. So we notified this previously from all of our social media platform. So deadline has been extended. So like if you are interested in contributing, you can register. We will send you email when there's interview round. So
I,
once
I also
again,
want to,
hmm?
yeah, I want to say thank you so much for this opportunity. I had really good time describing my research, but also for the incredible question answer session. I think this was the one of the very few session where I was like, oh, I have no idea about this thing, and potentially leading to collaborations, and yeah, just awesome session. So thank you so much
Yeah.
for
So
organizing this, and wish you all the best. Okay, keep doing this kind of sessions. I hope people find it very useful, and wish you the best for all the stuff that you are doing as a part of Zeta Gravit. So great job.
thank you. Thank you.